Alright, good morning, good afternoon, good evening, class. This is Mr. Aerosena, and today we're going to talk about temperature and heat transfer in my discussions in physics. Okay, so to get started, temperature and heat transfer in physics have a lot of very specific meanings, and we'll talk about each of those specific meanings when we get to it. But just keep that in mind that in physics, temperature and heat transfer and a lot of the words related to it all have very specific meanings. Similar to how we were discussing in the work unit that work in physics has a specific meaning which might be different than what you're used to. Anyways, to start off, we'll go back to the kinetic molecular theory, which, if I'm not mistaken, the last time you would have seen this would have been in, I think, Science 8. Maybe Science 9. They might have mentioned it in Science 9 a little bit. Anyways, the basic idea behind kinetic molecular theory is that all matter is made up of tiny particles that move. So if you remember from, I guess, Science 8, Science 9, solids are very, very compact molecules, don't move too much, and then when you become a liquid, you move more, and when you become a gas, you move like crazy. Anyways, what they neglected to tell you in those early science grades or early science classes was that molecules actually move in one of three ways, or a combination of these three ways. The first is translational movement, which is you're very familiar, just going back and forth, up, down, left, right, whatever. This is translational motion. The second way, and this one is a little harder to visualize, is rotational motion, which is basically how your object rotates in space, either rotating on an x-axis, a y-axis, or a z-axis, but it's just basically rotating. And the third way an object can move is through vibrations, and that's basically just vibrating in place like that, like this ball here, vibrating in place. Excuse me. This is rotation, and this is translational motion. Now, an object can possess all three, or can move in all three ways, as this next arrow will show you. So there is rotating, and now it's translating and vibrating all at the same time. So all objects, all particles in all objects move in either one of these three ways or a combination of these three ways. I should say they always move in a combination of these three ways. Okay. So now your particles are no longer limited to just moving forwards and backwards. They can now rotate and they can now vibrate. Okay. What does this mean for us? Well, it means that objects actually possess several different types of energy. Okay. The last unit we just talked about potential and kinetic energy, and I mentioned that there's really only one way to describe kinetic energy. Well, that's actually kind of not true. Since we know that an object can move in three different ways, translational, rotational, and vibrational, it can actually have three different kinetic energies. It can have translational kinetic energy, it can have rotational kinetic energy, and it can have vibrational kinetic energy. You can actually have a combination of all three, depending on how much energy the object has. And it still has potential energy. An object can still have potential energy. Now, in the last unit we only discussed really gravitational potential energy, and we discussed elastic potential energy. But here I mentioned that the potential energy between molecules can also come from attraction and repulsion through either electric repulsion, so in case of say like static charges or charges which are attracting or repelling from each other. Also come from attraction and repulsion of magnetic forces, so if things have a magnetic field, they can repel or attract each other. And gravitational forces, which if you guys take physics 12, you guys will learn all about how everything is attracted to everything else through gravity. Okay, so those are ways that an object can have potential energy. What we're going to focus on, though, really is, I guess, for this, is that these are all forms of kinetic energy. Forms of kinetic energy. Now, why don't we ever mention the rotational and the vibrational energy? Well, for the most part, they're pretty negligible on the grand scheme of things. So, for example, on our macro scale of existence, we don't actually have to worry about rotational or vibrational energy because the translational kinetic energy is so much bigger. So what you can say for most objects, so it's in most objects, the translational kinetic energy is much, 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 much greater than the rotational kinetic energy or the vibrational kinetic energy. Okay, this terminology here you might see in math class later. But basically just means that it is much, much, much greater to the point that my rotational kinetic energy and vibrational kinetic energy may as well be zero in relation to total kinetic energy. Okay. So when do these matter? Okay, pretty much only on an atomic scale. Okay, for the most part, only matters on the atomic scale, or I guess molecular scale, atomic molecular scale, atomic scale. Okay, so that's when the rotational and vibrational kinetic energy kind of matter if you're dealing with single atoms or just a finite, a very small number of atoms, because then they actually have significant amounts of rotational or vibrational energy, which could actually matter. Okay, but for the most part, we don't care about those two forms of kinetic energy because the translational kinetic energy tends to be a lot larger. Now, this does change our total energy equation because if you remember from last unit, total energy was just kinetic energy plus, so I guess it's right here. From last unit, total energy was just my kinetic energy plus potential energy. But since we have three different forms of kinetic energy, we can actually change the kinetic energy to the following. So total energy is just the total translational kinetic energy plus the total rotational kinetic energy plus the total vibrational kinetic energy and then plus the potential energy. Okay, and this is what we call thermal energy. Okay, and thermal energy is really just another name for total energy. Okay. So like I said, thermal energy has a very specific meaning in physics. In this case, it is total energy. Okay, so this thermal energy is really just another name for total energy. Okay. Now, thermal energy can be transferred. Okay, you know this very well. Anytime you touch something hot or anytime you touch something cold, you are transferring some of your energy, or you are transferring some of the energy from the hot object to your hand. Okay. This transfer of thermal energy is called heat. Okay, so heat is a transfer of thermal energy. Okay. Okay. So total energy is thermal energy is the total energy in the object, and if any of that thermal energy is transferred, that is called heat. Okay. Now, heat from observation has always been transferred from hot objects to cold objects, and in order for energy or in order for heat to be transferred, there needs to be a difference in temperature. Okay, so anytime there's a difference in temperature, heat will transfer from the hot object to the cool object. You can experience this yourself simply by touching a metal object in the room or in your chair or wherever you're sitting at. Just touch a metal object. The metal object will probably be at room temperature. Your hand is probably not at room temperature. So it's probably quite a few degrees warmer than room temperature. And when you touch the metal object, because the metal object is a very good conductor of heat, it will actually transfer heat from your hand to itself. And that's what you perceive as cold because you're losing heat. Anytime you lose heat, anytime you feel cold, that's when you are losing energy. Okay, when you are losing thermal energy. Now, some objects, even though they might be at room temperature and you touch them, they might not feel particularly cold or particularly hot, and that's because they are not conductors of heat. So they don't transfer heat easily. Okay, so they don't transfer. So when you touch those objects, the heat doesn't leave your body as quickly if you're touching a non-conductor. If you're touching a conductor, heat will leave your body quite quickly. Anyways, so those are our definitions of thermal energy and heat. They are not the same, but they are very closely related to each other. Now, temperature is related to these two, sort of. Temperature is, as defined in physics, is the average translational kinetic energy of all the molecules in some material. Okay, so note that it's only the translational kinetic energy. It's not the rotational and it's not the vibrational kinetic energy, just the translational kinetic energy. Okay, and a thermometer measures temperature simply by the movement of particles that collide with the thermometer. So if I were to draw a thermometer, so if this is my thermometer, I'll have particles moving towards it. Okay, and the number of collisions and how hard those collisions are will transfer energy to the thermometer. So here's my thermometer, the liquid inside the thermometer or the sensor inside the thermometer. And as these particles collide, they will either transfer energy and they will transfer energy to the particles inside the thermometer, and those particles will move up the thermometer. Or in the case of if it was a digital thermometer, it will just measure how the frequency and energy of collision when it hits it. And that movement is what determines the temperature because it's measuring the average translational kinetic energy of the materials hitting it. Yeah. It doesn't measure how much rotational energy or how much vibrational energy it has because again the translational kinetic energy is so much greater that that's what gets measured. Okay? That's what gets measured. Now temperature. We measure temperature in one of two ways, either in degrees Celsius or we measure it in degrees Kelvin. Okay. Degrees Celsius was a common scale, and degrees Kelvin is what we call an absolute scale. To convert from degrees Celsius to degrees Kelvin, simply add 273 degrees. And if you want to convert from degrees Kelvin to degrees Celsius, we subtract 273 degrees. For those of you from who've taken Chem 11 or are currently taking it, you'll probably see this conversion. Okay. All right, so that's how we measure temperature. Again, temperature is just the average translational kinetic energy of all the molecules in some material. Okay, a common question you will probably see is if you're given an iceberg, so iceberg versus hot iron nail. Let's go. This is hot iron nail. Okay, common question you'll see is between these two, which has a higher temperature, and which has a higher thermal energy. Okay. And quite simply, as long as you remember the definitions, this is really easy to answer. Which has a higher temperature? Well, the hot iron nail will probably have the higher temperature simply because its temperature will be greater than 0 or greater than 0 degrees Celsius. Hot iron nail will have temperatures of upwards of 100 to 200 degrees Celsius. Okay. Now, which has more thermal energy? Well, the iceberg, because it simply has more matter. It has more material, and having more material means that you're going to have more things with more energy. And since the iceberg is so colossal, so much larger than the iron nail, the iceberg will have more thermal energy. Now, each of the molecules in the iceberg will have less energy than the molecules in the iron nail, so that's why the iron nail has a higher temperature, because the average translational energy in the iron nail molecules is higher than the average translational energy in the iceberg molecules. Okay. So as long as you remember the definition of what is temperature, again, temperature being the average translational energy, And you remember the definition of thermal energy being that thermal energy is a total amount of energy in the substance, then this question is really easy. Or, yeah, it should be really easy to answer. Okay. All right. Okay, skip that. Okay, now, one concept that scientists like to talk about is absolute zero. If you remember from, I think this might have been mentioned in earlier science class, absolute zero is the point where your average translational kinetic energy is equal to zero. So basically, your molecule stops moving. Okay, so at absolute zero, you have no translational kinetic energy. However, this does not mean your object is stationary because your object can still have some amount of rotational energy and some amount of vibrational energy. Probably not a lot, but it does have some of that energy still present. Okay. And as our best guess is, absolute zero occurs at approximately minus 273 degrees Celsius, or at around 0 degrees Kelvin. When we're doing any kind of energy calculation, we tend to stick with the Kelvin scale because the Kelvin scale is an absolute scale again, starting from zero and going on up. If you use Celsius for some of our calculations, it makes for some really weird results. So anytime we do similar to how we did in chemistry when we're dealing with the gas laws, we always use a Kelvin scale. Same thing in physics. We'll use a Kelvin scale when dealing with temperature. Now, as I mentioned earlier, when talking about touching metal objects and being good conductors and whatnot, that's one way of transferring heat. Yeah, there's actually three ways of transferring heat, and we'll talk about all three of them today. The first way is by conduction, and this is quite simply when things touch, um, molecules from one object will collide with another object, and that active collision is what will transfer thermal energy. Okay, think of it like a ping pong ball, I guess. Or not ping pong ball. Pool ball is probably better. When one pool ball hits another pool ball, it transfers energy, and then that second pool ball gets hit. Okay, this is kind of what happens in conduction. So let's watch that again. One particle collides with another, transfers energy. That particle moves on, hits another particle, transfers energy. Right? So anytime particle collisions happen, thermal energy gets transferred. Now, this type of energy transfer works best in solids. And the reason for that is, if you remember how solids are arranged very, very close together. So solid atoms and solid molecules are arranged very closely together. And they allow collisions very easily. Okay? Conduction does not work very well in gases and liquids for similar reasons, because in a gas and a liquid, the particles aren't as close together, so particle collisions don't occur as frequently as they do in solids. That's not to say that liquids and gases can't transfer heat. They can actually transfer heat quite well, just not through conduction. Gases and liquids transfer heat through a process known as convection. Okay? Convection is the act of transferring heat in a gas or a liquid. And this happens because as a gas or a liquid moves, if there's a large amount of moving gas or moving liquid, they can they can carry with them a large amount of heat energy or a large amount of thermal energy. Okay? Convection is actually what is responsible for the world's weather patterns, because the large amount of moving air or moving water vapor can carry heat from one part of the world to another part of the world. Okay, and in the spirit of Earth Week, when this is recorded, the um, the convection currents in the Earth's atmosphere are actually carrying more heat now because they have a lot more stuff in them. A lot more stuff is dissolved in the atmosphere, so that stuff is able to collect heat and transfer it all around the world. Okay. Now, convection is very, very efficient compared to conduction in liquids and gases, because in liquids and gases you can move large amounts of liquids and gas molecules, so convection is the way to go. Okay. Now, the gas or liquid, as it moves, it can transfer thermal energy as it moves. Okay. Now, part of the reason for this is that if you have large movement of air or large movement of gas, there's a large number of particles, and when they collide with things, there's a large number of collisions. And then that act of colliding will transfer thermal energy. Yeah. One easy way to observe convection currents is if you happen to have a pot with a clear lid. And you cook some either frozen corn or frozen peas. You can see these convection currents here lifting the peas from the bottom to the top, or I guess corn, depending on what kind of frozen things you eat. You can sort of observe this as well with instant noodles, but not as easily. If you want to observe convection currents in a pot, best way is with just frozen peas or frozen corn. Okay. If you happen to live near a large body of water, I'm not sure if the lakes around town are large enough, but definitely if you were to live in, I think, around Fort St. James, I think, the Stewart Lake, I think, is large enough you can see this, is that um, during the day, especially if it's sunny, the sun will heat up the ground very quickly, and it will cause the air above the ground to rise, and then cool air above the water will come in and replace it. So if you're living near the shore, the wind will blow towards you. Now, yeah, at night, the opposite kind of occurs because water cools down longer, takes longer to cool down water. So at night, the air is warmer above the water, so that rises, and then the air is cool on the ground, so that rushes in to meet up. So then the wind will blow towards the lake. Okay. That's part of how some weather patterns occur. Okay. Right. The third way of heat transfer is through radiation. Radiation is any type of electromagnetic radiation that is emitted because of an object's temperature. The best example of this is basically infrared radiation from a heater or a light from an incandescent light bulb. Incandescent light bulbs, by the way, are very, very inefficient because most of the energy that goes into an incandescent light bulb gets turned into heat energy. Okay, great for heating up things near the light bulb, not so great for light. Okay. But anyways, so thermal radiation is just electromagnetic radiation, and this electromagnetic radiation will transfer heat energy from the hot object to the cool object. This is responsible for basically keeping the Earth warm because without infrared radiation from the sun, we would be a very, very cold rock floating in space. Okay. Now, one of the great things about thermal radiation is that it has the ability to travel anywhere. There's no need for it to have a medium. So unlike conduction, which works best in solids, or convection, which works best in liquids and gases, radiation doesn't need a solid, liquid, or gas to transfer energy. It just needs to travel from one place to another. The sun is a great example of this because traveling through the depths of space, there's not a lot of particles between here and the sun. It's a lot of empty space. So without this property of traveling in any medium, okay, the Earth would not get any energy from the sun. Okay? Now, this might make you think that thermal radiation is a great way to transfer energy from one object to another, or transfer thermal energy from one object to another. It can be, but there are certain things you can do to prevent it, because there are some cases where you want to prevent the transfer of thermal energy, or you want to prevent radiation from occurring. And through our observations and experiments, we've discovered that objects have the ability to reflect or absorb radiation. Okay? And generally, this is through what color the object is, or how shiny the object is. Okay. So for color, lightly colored objects or shiny objects will tend to reflect radiation. So for example, you'll probably experience this now that the weather's getting a little better. If you're wearing a dark coat on a sunny day, the dark coat will heat up quite quickly because it absorbs a lot of radiation from the sun on a sunny day. If you're wearing a lighter colored coat, the lighter colored coat tends to not heat up very much because it's lightly colored, so it doesn't absorb a lot of the radiation from the sun. Okay? Similar things will occur. For example, here, this person here is wearing his survival blanket. The reason why it is shiny like that is because if you wrap yourself up in it, any thermal radiation, any thermal energy that you are emitting because you are a warm body, the light, the shiny blanket will reflect back onto you. Okay. Here, this black car, for any of you guys who have a black car, you'll know this really well. Black cars tend to heat up very, very quickly on a sunny day. So when you touch the surface of the car, it tends to be quite warm. Other cars will exhibit this behavior as well because metal tends to be a very good conductor of heat. So even if it's a lightly colored metal, it'll still absorb some heat and it will still be quite hot. But for the most part, a lightly colored vehicle tends to not be very hot. Okay. If your car has a leather interior, it's amplified even more because a dark leather interior will absorb a lot of heat, both from the sun and the fact that the sun heats up the air inside the car. Yeah, dark leather interior on a hot summer day is very, very uncomfortable because it's very, very hot. A lightly colored leather interior, however, is slightly better. It might still be hot, but it won't be burning hot like a black leather interior. That's partly because dark colored objects tend to absorb radiation, whereas lightly colored objects tend to reflect radiation. Okay, and you'll experience this now that summer's coming up on us. You'll experience this as well, right? Especially if you like to wear dark clothing. If you wear dark clothing, you will probably get very hot during the day if it's sunny outside. If you wear lightly colored clothing, it's not so bad because light colors will tend to reflect the radiation. Okay. Anyways, there you go. So there's thermal energy and how thermal energy gets transferred from one object to another, and a couple of ways on how thermal energy is how thermal energy is transferred, okay, and what you can do to prevent radiation. Okay. All right. Okay. Your assignment for today then is as follows, and if you guys have any questions, you guys know how to contact me. Oh, one note. For question one on page 165, I think, you don't have to actually dismantle the thermos bottle, but if you do have a spare thermos bottle, do take it apart and see what it looks like on the inside, because it might be kind of interesting.